so ADMX, we've been doing a lot of this over the last year. This is getting the insert ready to go into the magnet. That's when the insert comes out of the unit. So you do that, you fix it, you do that, it goes back in, back and forth. Hopefully in there you take some Axion data. Right, so last talk of the day, I'm going to skip. We all know everything about the Axion, so I show you just a few more things to remind you. We think the Axion is a really good dark matter candidate. We think it's out there. We think that it's a QCD Axion and it lives on this line. And you see that I heard someone talking about how, oh, you know, this Axion experiments, they've been going for 30 years and they haven't seen anything yet. When do you give up? We haven't really been going for 30 years. We're just now getting into the theoretical promised land. So things are just getting exciting. As you well know, if things go on before inflation, the Axion mass could be anything. You could still get dark matter. After inflation, it's somewhat more constrained. For my motivation, I zoom in and say, well, what do the theorists actually predict? And I take a smattering of archive papers and I say, well, I don't really trust any of these people and they don't seem to agree with each other, but this is somewhere around here is where we ought to be looking. And so that's kind of where we start at the easy spot and work our way up. This is the group that I represent. This is the ADMX collaboration. The goal is to find the dark matter Axion. Here's what the experiment looks like. I will skip how a haloscope works. You know this already. But the ADMX haloscope, this is an 8 Tesla magnet. We have a cavity inside. Right now we have 2 moving rods to tune the frequency. So axions come in, turn into photons, come up here, go up into this quantum electronics package, which has its own magnet to give it a 0 field region. Everything else is refrigeration, insulation. And this is how we look for the Axion. So we tune the cavity to a certain frequency. We take 100 seconds integration time, make a power spectrum and look for a bump. Move the rods, change the frequency, move the rods, change the frequency, add all these up. So we get these spectra. So these are the background subtracted. And this is a synthetic signal we've injected. And you would see as you get to be on resonance, the signal grows, and as you get to be off resonance, the signal shrinks, and you add these in a sensible way. And hopefully at the end of the day, maybe at the end of 2 weeks, you get this peak and you say, aha, I found the Axion. Well, when we're tuning, the way we're moving this frequency band is on one hand moving these tuning rods in the cavity, shifting the resonant frequency, shifting the sensitive range, and our quantum amplifier, our Josephson parametric amplifier, also needs to be tuned. And perhaps the experts understand this plot, but this is a knob that I turn, and the interface here is where the JPA works, and so this has to match that. It's kind of a hassle, but we've got it working finally. So let's say we see one of these bumps. We have to figure out, is it an Axion or is it somebody's phone? Is it radio frequency interference, or is it one of those pesky synthetic Axion signals that our kind of secret team injects? And they inject these nearly once a megahertz. So every 2 weeks we look for candidate Axions. We always get about 10. And so it keeps us on our toes. But it's nice because it's that we're not biased. There's always going to be candidates, and so we're always exercising our procedure to determine if they're Axions. I won't go through the whole thing other than to point out that the signal has to persist. And it needs to be suppressed in other modes, and it needs to be proportional to the magnetic field squared. And as of yet, no signal or noise has made it through this entire process to finding the Axion. Since I have a short talk, I'll go straight to where's the current results from ADMX. These were presented last Patras. So this is a bit of review, though we got published in the middle and towards the end of the year. So Axion photon coupling frequency. Blue, orange, red is year after year after year. So we managed to cover more and more ground each year, though we've taken a break this last year for some upgrades. We've reached DFSZ in most cases. This region almost to DFSZ, and we're working on that. That's what we're doing right now. This is, of course, assuming standard dark matter density. We use 0.45 GeV for CC. If you want to know, well, supposing I truly believe in, say, a KSVZ Axion, what densities am I probing? You can make the same plot. And it looks like this, and you can see, and for KSVZ Axion, we're sensitive to even very, very subdominant fractions of dark matter being made of Axions. So good news for you WIMP hunters out there. Greater context. So here's that search space that I was talking about before. So coupling, mass, or frequency. And we're starting here, and we're marching our way up. We're starting to reach into these theoretical, exciting regions. You see there's still a long ways to go. You see I've managed this as this was presented at this conference. So it's been very lonely in the DFSC club, and I'm glad that's changed. So what we've been doing this last year, a lot of upgrades, a lot of improvements to noise, a lot of improvements to scan speed, a lot of, we ran very hard in 2020, and so 2021 was a lot of like maintaining things that had broke down during COVID. Hopefully the cavity will be cooler, getting better performance out of our JPA, getting better. It turns out that getting a low noise is only half the battle. The other half is proving you have a low noise, so working on better calibration of the noise. So where are we right now? So when I wake up every morning for this conference, I open my web browser, and the first thing I do is check the data taking page. And so right now we are operating in this frequency, and the plan for the summer is to see how much of this we can get down to DFSC, because that is our, that's the real goal. That's where you're going to find something, in my opinion. So we're going to work our way down as far as we can, but we're scheduled in October to pause and get the new cavity. The current cavity is getting kind of tired. This frequency range is getting kind of tired, and get the new cavity to work our way up. So that's, in our own terminology, this is called Run 1D. So these are 2021 results. Run 1D, which should last between a year and a half, will be covering up to this range at DFSZ. It's going to the rods are getting kind of big, right? We're getting to where our cavity is filled by a rod a lot. So after that, so we're looking a year and a half to 2 years out. We get the next cavity there, a 4-cavity system combined, power combined. And that lets us reach up here. Now things are getting difficult. The scan speeds get slower and slower and slower towards the end for various reasons discussed previously in the workshop. So moving beyond this, we need a serious upgrade. And the set upgrade is called ADMX Extended Frequency Range. They make us give these things silly names, and this would be taking this would be taking us from 2 gigahertz to 4 gigahertz. We need a bigger volume. We need a bigger magnet. We're finalizing the design, but to accommodate this magnet, the intention now is to move it to Fermilab. This is the engineer's conception of what the experiment looks like. It's different, right? So here's this MRI magnet. It's horizontal bore. That's unlike what we have now. We have to move to arrays of resonators. So this is mini cavities, all power combined. So this next step where we do 4 cavities combined is going to be a critical to prove that, because we need to prove that we can do 4 before we can move on to 16. We're going to separate out our low noise amplifiers into a separate dilution refrigerator, and the engineers swear they can make this a very, very low loss run. So updates on this, we have the magnet already. So that's part of it. Of course, you would like to buy and build a magnet, but that takes a very, very long time. It's easier to find a magnet, and this is an MRI, so 80 centimeter bore. You can crawl around, and there's lots of space. 9.4 Tesla. I believe it was running at University of Illinois, and they've ramped it down. And we have to kind of come in the dead of night, knock down a wall, and bring it on a truck and bring it over to Fermilab, and then we're good to go. The cavity array is an interesting project. If you want to talk to Stefan or Ben, they did a lot of the work in understanding what is our coupling to the Axion in this. So each one of these is a cavity, and they fit together like a honeycomb. And this for those who aren't deep into the field, is a measure of how well you couple the Axion. And it's very important that you can predict this accurately, and you can see we know how we're going to scan over this range. You get these mode crossings are always a problem, and I believe these can be eliminated by using slightly different length cavities. So anyhow, this is 250 liters, and notice we're using this is an experiment we can do with pretty old technology, right? Q of 60,000. We've heard a lot of really interesting developments, and I hope I get a chance to contact you and incorporate these. It would make for a much better experiment. One last slide about R&D. So we have been in the current experiment, we have this sidecar system that's stuck on the side where we get to demonstrate a little bit of new technology, and we have recently demonstrated that we can use one of these traveling wave parametric amplifiers. So there's a gain curve. And I believe the students are taking Axion data with this right now as well. But the point is, look, this is 3 to 8 gigahertz, decent gain over 3 to 8 gigahertz. No more of this tuning your JPA and always the cavity and JP aligned. Should make operations a lot easier and a lot faster. It's it doesn't get discussed much because it's kind of boring, but in the end, for your Axion experiment, the actual operations cadence, like how much live time do I have versus how much time am I tuning the rods, how much time am I spending with the amplifiers, turns out to be critical if you're trying to cover wide frequency ranges. So with that, I've tried to go very fast because I had some questions about this US Snowmass process. So every 10 years, so we were moving away from ADMX to talking about the funding system in the US. Every 10 years, the high energy physics community gets together and makes a big document that advises the funding agencies of what their needs are for the next 10 years. And it culminates with this, with a big meeting where everyone kind of shows their slides and their documents, and people argue about the wording. It's not super fun, but it's necessary. There it is in Seattle. This was just a few weeks ago. I had the honor or the misfortune of representing the Wavelike Dark Matter community. That's to say, people looking for dark matter less than an EV. So this was me, this was Jorg, and this is Lindley Winslow as a team to try and contact everyone doing experiments in the US and ask, okay, what do you need? What's one very simple message that we can to the funding agencies? I mean, they have only a few neurons to devote to us, so we have to have a very simple message. This is the message that we developed in coordination with the community. We said, look, number one is this decade, as opposed to last decade, we have the technology to reach the QCD Axion at DFSC. That should be a major target, and the current experiments going there should get funded. They should get funded fast, and we should have a program to reach DFSC as far out in masses in every direction. So that's number one. Then number two was we are not an accelerator. We do not necessarily need one big project. There's different technologies, different frequencies. We need programs to fund small-scale experiments. Number three is support enabling technologies. So this is superconducting cavities, quantum amplifiers, better NMR, all of these that we had a list of these technologies that are important to the Axion and scalar and vector program. And then finally, support, still we need theory support, especially beyond the QCD Axion. There are a lot of experiments out there that are sensitive to scalars and vectors, and we would do well to have some theoretical guidance to say, well, where should we look? What should we focus on? Should we just look everywhere all at once? Well, maybe there's something that's easier or better. So that's our message, and here's the US program that we kind of envisioned. So existing limits, this is, if you were to say, in the QCD band, what have we got so far? Well, we're just starting out. There's this ADMX EFR, you heard about DM radio meter cubed. These are in the queue, not funded, but sort of hopefully waiting in line. And so we encourage those to get going as quickly as they can to cover a decent chunk of the Axion mass range. And then this host of experiments that need somewhere between R&D and small-scale funding in the next 5 years to hopefully get into bigger and bigger projects to cover the entire Axion mass range. There was also something that came up in the meeting. A number of people said, to get better attention, we should be asking for a $100 million facility, because everyone here, almost everyone here, not quite everyone, needs really big magnets. Big high-field magnets, great big bore. And so there was some talk of, hey, does the community want to really get behind saying, one of these national labs gets a whole bunch of magnets, great big bore, and the infrastructure, and then these smaller groups come in and run in there, like a beam line. The magnet is the beam line, and it's equipped to build your Axion experiment, put it in like these beamline detectors. If that's something people are excited about, feel free to talk to me and give me encouragement. And I mean, this is a far view project, right? If you're asking for that much money, you have to make noises to the funding agency, and then first the funding agency will say no, and then they'll laugh at you, and eventually they give you money. But it may be something we need to start now. So for those who are still interested, we composed these. I mean, we edited, let's say, these white papers. One specifically targeting axions, one on scalars, vectors, other ultralights. And we tried to gather as much as the US community and also the international community to write these. And then finally, there'll be one paper combining these and putting them into an executive summary that passes along to the So we are in the Wavelike Dark Matter subgroup. There is the Cosmic Frontier subgroup. It's important to get our message in their white paper, and then they go to the Snowmass, all Frontier white paper. So we have to craft something that makes its way up, and then it goes into the prioritization panel, and we hope to be high priority. So I've gone very fast because it was a very, very short talk, but I wanted to leave lots of room for questions. Just my commentary is it was really exciting to be back at Patras, and I'm really excited to see. So the last time I was at Patras in person, there were a lot of crazy ideas, and they were just ideas, and they were all talk. And this time, that talk has turned into data. That's turned into hardware. I'm really excited to see that. When I say, oh yes, we're gonna cover this whole Axion mass range, I think I kind of believe it now, you know. Anyway, so thank you. Let's move to questions.
That's great. So questions. There's one here.
So in your search range, especially that orange one, there was a big gap. So why is that?
So for example, in this coupling to Axions, these mode crossings happen when you have perhaps a TE mode and a TM mode that as you tune become the same frequency, the same, this is what avoided level crossing as you'd call in condensed matter. So that's true in any cavity. And in our results here, that was a big nasty mode crossing. And if you go into your simulations, you cannot get high confidence that you have good coupling the Axion. You don't scan there. So someone's got to come back and look there to be comprehensive.
So that's what the Axion is.
Well, I mean, a follow-up question is like, oh, well, shouldn't you stop, rebuild a cavity, and go look there? But the question is we want to discover this thing. We want to cover the maximum space in the minimum time, and it's probably faster to look there. If you have a year, you spend your year looking over wide unexplored space rather than tooling something just to cover this gap. However, for those of you building small experiments, test beds where you're covering a narrow frequency range, feel free to check in with me. And if in this frequency range, I can say, oh, we have this mode crossing here. It would be really great if someone just covered this little range. I think that would, as a community, it would be great to kind of mop that up. You could get lucky.
Great, that's a great idea, actually, because we never report in detail our mode crossings, and maybe we should.
Yeah, I feel like in our latest PRL, we try to say here are the regions that are gaps, but if we don't, we should, and if not in a PRL, at least a appendix, because that's someone then gets to cite that and say, hey, I built this thing in my basement, and yeah, it didn't have wide range, but it did cover something technically unexplored.
So David.
Thanks. So you talk about injecting the fake signals, but presumably when you do have a fake signal and you open the letter and it says this was a fake, do you then go back and scan that frequency without a fake signal?
Yes.
To make sure that the Axion wasn't hiding under your injected signal?
I mean, the odds of this happening are very, very low, right? But yeah, we do in the process of going back and looking, rescan that area. I'm going to the slide that shows that this is kind of a really fun thing we did where the synthetic injectors put in a signal and the operators looked at the signal with both the TM010 mode, which couples well to the Axion, and the 011 mode, which should have zero coupling to the Axion. And you saw the signal in both, which means we could tell it was not a real Axion. So yeah, we go back and rescan this over and over and over again, and they open the box, and you scan it one more time, just to check.
Hi, so thanks for the really great talk. So just really quick, two really quick questions. First of all, how long does it take you to tune the rods basically to a different frequency? And what's the overall duty cycle, say, for a day? And secondly, in your slides number, I think it was 15, you say you have a 4-cavity system, which is power combined. So do you also use phase matching with these 4 cavities? Are they like similar cavities, or they work in different frequencies?
Right. Okay, so that's 2 separate questions. One is the data taking cadence. Let's say naively, a regular cadence is 100 seconds of digitization, 2 seconds for a transmission measurement, 2 seconds for a reflection measurement. Tuning the rods is about a half second currently. And then out of that, if depending on how well the quantum amplifier is it could be up to it could be an average of 30 seconds to make sure that you have good noise and it's at the right frequency. So that's why I say I was excited about a wideband amplifier. As you see, that's eating up some of our lifetime. So that gives you a lifetime of 60% in normal operations, and then plus all of the regular downtime that experimentalists know about. Second question was the cavities. So in a multi-cavity system, if I understood your question correctly, so to get maximum benefit from the cavities, they have to be tuned to the same frequency, and you have to add the power in phase, and that gives you an order in improvement of signal. If you just drive your cavities wherever and you add their results, you get an order square root of n, which is better than nothing, but that's when you've got 16, you want to get all 16 in phase, and that's a significant engineering challenge that we believe we can meet.
Okay, thank you very much.